Labyrinthodon. Spell it. L-E-B-Y. Yeah, that's right. Inthodons. And the Lyssamphibia. Now, the Labyrinthodons are all extinct. And at one time, all extinct amphibians were put into this group, and it was considered a subclass. With a lot of molecular analysis and other analyses of fossils, people have decided that that's probably not a single subclass. It's probably broken up into many groups. In other words, it's polyphyletic. But you'll still see this term Labyrinthodon used consistently to refer to the ancient amphibians, the first ones to come out onto the land. The Lyssamphibia, in contrast, is all of our living amphibians. So within that, we have the Urodela, or the Caudata, the Anurans, and the Apodons. So the UR part is referring to the Greek word for tail. If you use the term caudata, cauda is the Latin word for tail. So these are the tailed amphibians, or the salamanders. The A, or AN in this case, means without, coming from the Latin. So without a tail. The Anurans are the amphibians without tails. They are the frogs and toads. A, again, meaning without, pod meaning foot. The legless amphibians, the Sicilians, sometimes called the Apodons. Okay? All right, where did amphibians come from? In other words, where did the Labyrinthodons come from? Well, we've already mentioned that the ancestral group of fish was probably the Rhipidiscians. And if you look in your book, they're using the term Tetrapoda morpha. So you may not see the term Rhipidiscian too often in the book. They use Tetrapoda morpha more often than Rhipidiscian. But if you remember, these are Sarcopterygian fishes, so the fleshy thin fishes. And why do we think then that amphibians, terrestrial vertebrates, came from this particular group of fishes? Well, there's a number of different lines of evidence that are used to suggest that. First off, we could have the structure of the limbs. There are some broad similarities in the structure of the limb of these Rhipidiscian fishes and the earliest tetrapods, the earliest land-dwelling vertebrates. And we can see that on, this is on the second page of your handouts. Come on. Anyway, so on the left, what you have is the skeletal structure of the front limb of a Rhipidiscian fish. Here they're just using the word Crossopterygian. And then on the right side, you have the limb of an ancient amphibian. And it's not too difficult to see how, with just a few structural changes, you can go from one to the other. If you look at the limb structure of other fishes that you might think could potentially be on the line towards vertebrates, their structure is very different. So example, Polypterus, which does have lungs. If you look at their limb, it looks something like this in structure. Right? Very different from what we find in the Rhipidiscian fishes. If you look at lungfishes, theirs looks something like this. So a very different pattern of bones compared to what we see in the early amphibians. Whereas when we look at these rhipidestian fishes, it is somewhat similar. It's much more easy to conceive how you can go from one to the other. So there's similarities in the structure of the limbs. There's similarity in the pattern of skull bones and the lateral line organs in the head. And just what I'm talking about is from fossils, you can get the fossil head of an animal, and you can identify individual bones that are inside or making up that skull. Right? I've only got the one here of an amphibian, but the point is you can go to the rhipidestian fishes and then compare their pattern of bones to that in these ancient amphibians, and there's a lot of similarity between them, less similarity with other groups. Also, the lateral line organ. So you've heard of the lateral line organ. We didn't go into detail on the fishes. It does run up and down the sides of fish. But that same structure, that same sense organ, is found in the head region. And in many animals, it's highly concentrated in the head region. And it leaves behind grooves in these bones that are forming the surface of the skull. So if you looked at the handout, you're seeing the little dashed lines right there and right there. Here's another one over here. Okay, there's another one right there. Those are locations of where lateral line organs were in this fossil animal. And so the pattern of the bones and the pattern of the location of those lateral line organs is similar in rhipidestian fishes and these very early labyrinthodont amphibians. Another similarity comes in tooth structure. The teeth of both groups turn out to be somewhat bullet-shaped, like so. And if you looked at it from the side, there would be a lot of indentations. So that if we took a cross-section of that tooth, it might look something like that. And if you look at that handout, what that is showing you then is this type of tooth, so that we have a rhipidestian fish tooth on the left, and we have the tooth of a labyrinthodont amphibian on the right. And you can see that close similarity between those two groups. So, based upon fossil evidence, it's pretty clear where the terrestrial vertebrates came from. They came from that group of rhipidestian fishes, or the Tetrapodomorpha, if you want to call them that. So we can see some similarities in the limb structure, the skull structure, the lateral location of lateral line organs, and the structure of the teeth. All of these things suggest that that's where the labyrinthodonts came from. Right. So we got some animals coming out onto land. Why? Okay, what's the benefit of coming out onto land? So what would be the selective advantage of doing so? There are two major theories as to why vertebrates first started to occupy a terrestrial environment. You can have the classical theory put forth by a guy named Romer. And this is basically a climatic theory. What Romer suggests is that during the time period when we know from the fossil record that amphibians first came onto land, that's the Devonian period, we know that the Devonian was fairly arid. And there's geologic evidence to suggest this. There are things, for example, called red beds. These are just particular layers of rock that contain iron compounds. And these iron compounds then are put down into the sediments and eventually form rock. But in order to get them to turn red, those rocks have to be exposed to the air. And they're not exposed to the air when they're deep down below the ocean. Right? So the fact that these sediments are becoming exposed to the air, causing them to oxidize and become red, suggests that we might have an arid period where water is evaporating, exposing the sediments, and then covering it up again, exposing it again. The Devonian also is a time of the formation of many evaporites. Anybody take geology? What's an evaporite?
It would be a sedimentary rock that's forming because of, I don't know, maybe I'm thinking of precipitation.
Well, it is going to be a rock, and it is formed by evaporation. That's the word evaporite. So salt, for example, which is the mineral halite, that is formed when ocean water evaporates and leaves behind the salt. So underneath the city of Detroit, where there are Devonian beds of salt, and we still have salt mines operating under the city of Detroit. Gypsum is another mineral that is formed through evaporation. It's a calcium magnesium sulfate mineral. Right? We have Devonian beds of gypsum underneath Grand Rapids that are being mined. Well, you're getting evaporation occurring if you're in a fairly arid environment. So the fossil evidence, the geological evidence from these red beds and from the formation of evaporites suggests that it was a very arid period. Okay. Well, Romer believed that they were probably, in other words, the ancestors of the first amphibians were probably air-breathing. And why does he think this? Well, because we're hypothesizing that the seas are warm and shallow. It's a period of aridity. We're exposing our sediments to the air. That means things are drying up, so it's reasonable to assume that it's fairly warm and it's fairly shallow. All right, you're not going to evaporate quickly a mile's worth of ocean, but if the water is very shallow, then you can see how these things might happen. You might be able to get your evaporites or your red beds. Why does it make sense then that we might have air breathing going on in this kind of habitat environment?
Because
Warm water with high salinity.
Yeah, warm water, high salinity, you're not going to have a lot of oxygen in it. So it's reasonable to assume that the fishes that were living at that time may have adapted to air breathing. All right. Also looks at the limb morphology of the ancient fishes and the first amphibians. And he supposes that they probably could sort of walk on the bottom of the pond, walk on the bottom of the ocean, across the substrate. So if you look at the limb structure of the lungfish today, their fin form, if you will, is very different. And these animals do sort of move themselves across the bottom using their fins in a somewhat of a walking motion. So he's saying that they have some pre-adaptations, if you will, to come out on the land. It's reasonable to assume that they were air-breathing, and based upon the structure of the fossil fins and based upon the fin structure and operation in some living ancient fishes, it seems reasonable that they might have been pre-adapted to a walking motion. So basically it's all coming down to the fact that the climate is warm, you're evaporating the water, these animals then are being found in small pools. Those pools dry up, the animal has no choice but to go overland to find another pool. So the first impetus, if you will, to go onto the land was to escape the drying up of the fish's pond in order.